if you've studied Pythagoras' formula, you will know that for a right-angled triangle with side lengths A, B and C as shown, the formula is a squared plus b squared equals c squared. What that means is that the areas of the squares on the side lengths of the right-angled triangle follow the relationship that the sum of the areas of the two smaller squares is equal to the area of the larger square. In this case, on the diagram on the right, the green area and the pink area is equal to the area of the blue. In other words, area A squared plus area B squared is equal to area C squared. And just to show that using some values, let's suppose that our three side lengths are A equals 3, B equals 4 and C equals 5. The units, of course, could be any units of measurement, centimeters, meters, and so on. Then the relationship a squared plus b squared equals c squared gives us 3 squared plus 4 squared equals 5 squared. And showing that as a diagram, of course, you can see that we have a squared, which is a 3 by 3 squared, which consists of 9 square units. B squared is a square consisting of 16 square units, 4 times 4, and C squared is a square consisting of 25 units, 5 by 5. But here's the question: does Pythagoras' formula hold when the side lengths are not squares? In other words, what about if we had circles as shown, where the diameter of each circle is the same as its corresponding side length? In this case, the diameter of the yellow circle is 3, the diameter of the blue circle is 4, and the diameter of the green circle is 5. Would we still have some sort of relationship like a squared plus b squared equals c squared? Here's one way of testing it. We can subdivide each circle into squares of any size, as shown, and then count how many squares there are in each circle. In the yellow circle, as a rough estimate, there are 7 squares. There are 12 squares in the blue circle and 19 squares in the green circle. So we have that 7 plus 12 equals 19. In other words, the sum of the area of the two smaller circles is equal to the area of the large circle. So it seems to hold for this example. To work out the exact values of the areas correct to 2 decimal places, we can of course use the formula for the area of a circle, pi r squared. So for the area of the yellow circle, the radius would be half of 3, which is 1.5, so the area would be pi times 1.5 squared, which is about 7.07. We can do the same thing for the area of the blue square. The radius is half of 4, which is 2. So the area is pi times 2 squared, which is 12.57. And for the green circle, the radius is half of 5, which is 2.5. So the area becomes pi times 2.5 squared, which is 19.64. And we can see that the relationship a squared plus b squared equals c squared holds, because we have 7.07 plus 12.57, which equals 19.64, which is the area of the larger circle. What about if the side lengths were triangles rather than squares or circles, as shown? Again, we can subdivide each shape, each triangle, and count the number of squares. And for this one, there are about 4 squares in the yellow triangle, 7 in the blue triangle, and 11 in the green. And 4 plus 7 is 11. So it seems to work again. To work out the exact values for the area of each triangle, we can use the formula for the area of a triangle, a half times the base times the height. And the height of each triangle is calculated using Pythagoras' formula. And as we can see on the right hand side, it works because we have the exact value to be 3.90 plus 6.93 equals 10.83. What about a hexagon? 6-sided shape on the sides. We can see on the screen firstly estimates for each area of each hexagon. 23 for the smallest, 42 for the next one, and 65 for the larger hexagon. And the relationship works. We have 23 plus 42 equals 65. and the exact values also seem to work. Can we generalize this? We can state that the theorem holds for all circles and for all regular polygons. But how do we show that? Let's prove it firstly for circles. In the diagram, as we've seen before, we have three circles representing each side of the right angled triangle. The area of circle A will be pi r squared, where the radius is a half of A, and the area comes out to be pi A squared over 4. Similarly, we can do the same thing to work out the area of B, which comes out to be pi B squared on 4, and area C will be pi C squared on 4. We can now add the two areas, area A plus area B, and when simplified gives us, as we have on the right hand side, pi bracket A squared plus B squared over 4. But we know from Pythagoras' formula that a squared plus b squared equals c squared, so we can replace a squared plus b squared in the previous line by c squared, and we obtain area A plus area B equals pi c squared on 4, which is the same as area C that we calculated in the second line. Now we can show that it is also true for regular polygons. To do this, we rely on a formula that is well known, which is the area of a polygon of n sides and whose side length is s. And the formula is that the area is given by s squared n over 4 tan of 180 over n. Now, for any given polygon with a given number of sides, the expression n over 4 tan 180 over n is a number, a constant. Let's call it k. So we can replace that part of the expression for the area of the polygon by k, and we can obtain that the area of a regular polygon is equal to ks squared. Let's keep that in mind for the next section. Let's suppose we want to see if the formula holds for this shape. We have hexagons. We know that the area of each hexagon will be of the form ks squared. Area A will be k times 3 squared because the side length is 3 units, so we have 9k squared. Area B will be k times 4 squared because each side is 4 units in length, so it becomes 16k squared. And area C will be k times 5 squared, which is 25k squared. Now adding area A to area B, we obtain 9k squared plus 16k squared, which equals 25k squared. But we already know that area C is equal to 25k squared. So we can conclude that area A plus area B equals area C, again confirming Pythagoras' formula.